The Automotive Information (AI) module of the Asvab tests your understanding of automotive maintenance, troubleshooting, and repair. The questions gauge your knowledge of automotive components and systems, tools, terminology, and common practices. Most high school automotive curriculums cover the information that this module tests. If you are taking the MET site or student Asvab, the Auto Shop (AS) module combines the automotive and shop modules into one that contains 25 questions, which you need to answer in 11 minutes. If you are taking the CAT Asvab, automotive and shop are separate modules. In this case, the Automotive Information (AI) has 11 questions that you must answer in 6 minutes. To achieve your 70% on the MET site and student Asvab, you need to answer 18 questions correctly, and to achieve 80%, you need to answer 20 questions correctly. Those scores are 8 and 9 correct questions, respectively, for the CAT Asvab. Again, the material in this module isn't hard, you just have to know the information that it covers. One advantage of the automotive module is that the names of auto components usually indicate what they do, so that makes it a little easier. However, the troubleshooting and engine operation section of the module might give you some problems if you haven't studied. You have less than a minute per question in this module, so don't let it bog you down too much. If you need extra help in this area, try to get a textbook from your high school auto class, or consult the information listed in Appendix B. Need to know more? A look under the hood. Just like a computer, a vehicle is a set of components and systems. Each system interacts to power the automobile. The ignition and electrical systems provide primary power to create energy and activate the other automotive systems. The engine systems create the force to move the vehicle. The best way to get a feel for where automotive components are located is to have a look. Before you do, make sure your car is off and the parking brake is on, then you can proceed safely. Next, carefully open your hood covering the engine and other systems, and take a look. Next, lie down on the ground and have a look under your car. This is the area where you can see most of the components that provide motion to your car. A word on safety. Before we discuss the tools and components of the automobile, it is important to touch on a few vital safety practices and considerations. Always wear safety glasses whenever you are working on a car, especially when you are doing metal work. Always wear a back brace and bend your knees when you are lifting heavy equipment or components. Don't try to lift more than you can handle. Always use the proper tool for any particular job. Using the wrong tool can result in injury or even fatality. Don't wear loose clothing or jewelry when you are working on an automobile. Work coveralls are the best clothing. You could potentially get your clothes caught on a tool or component, and you could be injured as a result. If you are working with heavy components or equipment, wear safety shoes to protect your feet in case you drop something, or something falls unexpectedly. Never work under a vehicle alone. If a heavy component such as an engine or transmission falls, or the car comes off the jack, it might result in serious injury or fatality. Having someone to help you or call for emergency services could mean the difference between life and death. When you jack up an automobile, be sure that you don't use just any car jack. Use the correct one for the job. Some are lightweight and others are heavy duty. Make sure you also use a jack stand and wheel chocks for extra or increased safety. Tools of the trade. As with many other professions, auto mechanics must have their own set of tools. You might be familiar with some of them, whereas others might be new to you, depending on whether you have automotive experience. Exam alert. Make sure that you are familiar with the most common hand and power tools that automotive work entails. Because Chapter 8, Shop Information, already discussed the common hand tools, we simply mention them here. These types of tools most commonly comprise an automotive tool kit. Hand tools and metalworking tools. Power tools, electrical, compressed air, and hydraulic. Cleaning tools. Measuring tools. A variety of threaded and non-threaded fasteners. Hand tools. Hand tools do not require any force, electrical or hydraulic, other than the use of your hands and your own physical strength. Of course, like all the tools you learned about in Chapter 7, most, if not all, hand tools multiply the power you exert upon them. These tools are most often used in automotive maintenance and repair. Box, open-end, Allen, pipe, and socket wrenches. Screwdrivers. Several types of pliers, including vice grips. Hammers. Starting pin and aligning punches. You will also find many metalworking tools in an automotive shop, such as files, hacksaws, chisels, drills, reamers, taps, and dies to cut and shape metal. Power tools. Although you can do the same job with a hand tool, power tools and equipment make jobs easier and faster, especially if you have repetitive work that requires a lot of your physical energy to perform. A power tool can operate by electricity, air, pneumatic, or hydraulic power. In this section, we discuss the power tools and equipment used most often for automotive maintenance. Electric power tools. Most specialized automotive equipment, such as oscilloscopes and wheel balancers, operate on electrical power, as do these types of tools. Electric wrenches attach to heavy-duty sockets via a socket drive on the wrench. Pressing the trigger spins the drive and socket to tighten or loosen bolts and nuts. Electric wrenches are especially useful for parts that have a lot of bolts and nuts, such as engines and transmissions. Electric drills drive a chuck that holds a drill bit or drives engine cylinder hones, deglazers, and brake hones. Electric drills can also drive screwdriver bits and sockets, but they provide substantially less torque than does an electric wrench. Grinders have an electric motor that drives a grinding wheel to sharpen tools, or a wire wheel to clean components. Compressed air power tools. Most automotive shops use an air compressor that draws in air, compresses it, and stores it in a tank. Air lines from the tank distribute the compressed air throughout an automotive shop or garage for tasks, such as inflating tires, blowing off parts during cleaning, and powering pneumatic tools. Air impact wrenches have a wrench assembly that connects to removable sockets. Many air wrenches also have an impact feature that drives the socket and vibrates it in and out. The force of the impact helps to loosen difficult to remove bolts and nuts. Air-operated jacks sit on the shop floor and raise only the front or rear of an automobile. Lifts raise the entire automobile to allow work underneath. The lift mechanism is below the shop floor to allow the vehicle to roll onto the lift. A single-post lift can adjust for any size vehicle by moving the four-wheel pads, while a two-post lift adjusts to lift the vehicle from the ends or the sides. Hydraulic power tools. Hydraulic tools use a lever and piston to pump and pressurize hydraulic fluid, and then use that pressure to greatly multiply the applied mechanical force. These are most common hydraulic tools. Hydraulic floor jacks pump hydraulic fluid to lift the jack pad and raise an automobile, and a control knob releases the fluid to lower the jack. To avoid damaging your bumpers and causing possibly serious injury to yourself or others, never jack up your car by the bumper, and always use jack stands with floor jacks. Caution. Mobile floor cranes lift very heavy loads, such as engines. Wheels allow the crane to be rolled into place. A lift chain or cable attaches to the engine, and the mechanic uses a control knob to raise the engine out of the vehicle. A hydraulic press consists of a hydraulic cylinder mounted to a table. Pumping the cylinder handle lowers a pressing ram with several tons of force to press bearings on and off shafts, or in and out of housings, or to straighten bent components. Cleaning equipment. Cleaning is an important step in almost all repair jobs, because the mechanic must clean the part before he can find problems and measure for wear. Common cleaning equipment includes the following. Steam cleaners generate steam to force soap solution over the part, to remove grease and sludge. Portable or stationary cleaners generate steam by burning natural gas or kerosene, and are normally for outside use. Solvent cleaners are for small components and parts. The solvent thins grease, oil, and sludge and washes it away. The cleaner circulates the solvent through a filter to remove impurities for reuse. Cold tank cleaners contain a soaking solution that removes carbon and paint from non-ferrous metal parts, such as carburetors or aluminum engine parts. You must use a face shield and rubber gloves when using a cold tank. Hot tank cleaners use natural gas to heat the solution for cleaning large ferrous metal parts, such as engine blocks and cylinder heads. Most hot tank solutions are strong enough to dissolve non-ferrous metals, such as aluminum. Glass bead blasters use compressed air and very small glass beads to further clean carbon and paint from parts that have been soaked in a hot or cold tank. Blast tanks can also use sand to clean parts. But the disadvantage of the sand is that it is small enough to become lodged in the crevices of the parts and inhibit movement and increase wear. Engine classifications. Now that we have covered the preliminaries, let's discuss the construction and purpose of the different automotive systems, starting with the engine. Legacy and new automotive engines can be classified in many different ways. Combustion type and combustion chamber shape. Number and arrangement of cylinders. Valve arrangement. Number of stroke cycles. Cooling system. Carburation methods. We examine each of these classifications throughout the rest of this chapter. Combustion types and chamber shapes. Engine combustion is the process of igniting and burning the air-fuel mixture to produce energy. This process can take place either inside, internal, or outside, external, the engine block. The types of combustion are as follows. Internal combustion. Most engines today are internal combustion engines. Fuel is ignited and burned inside the same container where the power is developed, inside the engine. The air-fuel mix is injected into the combustion chamber and allowed to vaporize briefly before it is ignited. External combustion. The steam engine is an example of an external combustion engine. In this type, the burning air-fuel mixture heats water in a container, and the resulting steam is piped into the engine to develop power. In a steam engine, the fuel can be burned almost anywhere, as long as it turns water into steam to send to the engine. Engines can also be classified by the shape of the combustion chamber. Overhead valve engines can have a hemispherical, wedge-shaped combustion chamber, or a pre-combustion chamber, which we discuss in the following sections. Hemispherical, or hemi-combustion chamber, places the valves on a slant at either side of the chamber and the spark plug at the center of the chamber. The design of the Hemi engine provides efficient air-fuel mixture burn-off at high speeds. Wedge combustion chamber design causes the piston to squeeze the air-fuel mix into the chamber in a swirling manner that gives good distribution for complete and smooth burning of the air-fuel mixture. Pre-combustion chambers, common in diesel engines and some gasoline engines. This design connects a second, smaller chamber to the main combustion chamber. On a diesel engine power stroke, fuel is injected into the pre-combustion chamber. Gasoline engines use a second intake valve, and combustion starts, and then spreads into the main chamber by its own energy. Cylinder arrangements. You can also classify engines according to the number of cylinders they have or by the arrangement of the cylinders, see Figure 9.1. Historically, engines have been produced with varying number of cylinders and in different arrangements for different reasons, such as to provide more engine power output, smoother running, or better fuel efficiency, or to accommodate space limitations. For inline arrangements, the cylinders are numbered with the cylinder nearest the front of the engine being 1 and the others numbered 2, 3, 4, and so on, front to rear. In V-type engines, the numbering sequence varies by manufacturer, but is detailed in the manufacturer's manual. The firing order, different from the cylinder number, is the order in which the cylinders begin a cycle. It is usually stamped on the cylinder block, but can be observed by the order in which the intake valves open. Inline arrangement. V arrangement. Opposed arrangement. Inline. If the cylinders are configured in a single row, you have an inline cylinder arrangement. They can be completely vertical or slanted to lower the engine's height. Although the inline arrangement works well with 4 cylinders, it is more difficult to evenly distribute the air-fuel mixture with 6 cylinders and even more so with 8. In addition, more cylinders mean longer engine length, resulting in a larger hood area and less passenger space. Inline is common in both cars and trucks, usually built in 4 or 6 cylinder configurations. V arrangement. In a V arrangement, you will see 2 rows of cylinders in a V-shaped block. Pistons from both rows connect to one crankshaft in the bottom of the V. Any even number of cylinders is possible in the V design. Motorcycles commonly use a V2, whereas automobiles and trucks can be VSIXS or V8s, and some V12s and V16s have also been made. The V design provides a shorter, more rigid engine and better air-fuel mixture distribution. Opposed cylinder arrangement. Opposed, flat, cylinder designs are common when the engine must fit in a small compartment at the rear of the car. In this design, 2 rows of cylinders are 180 degrees opposite each other on a flat plane, and the 2 rows of pistons connect to a single crankshaft located between them. Radial arrangement. This arrangement places the cylinders in a circle around the crankshaft, and is used almost exclusively in aircraft engines. Valve arrangement. You can also classify engines according to valve arrangement, of which there are 2 primary designs, the L-head and the I-head. A third design, the overhead, is an extension of the I-head. L-head. The L-head arrangement is an older design that places the entire valve operating mechanism in the cylinder block, allowing the cylinder heads to be very flat. The camshaft operates a set of valve lifters that push directly on the valves to open them high for good breathing, meaning that the combustion chamber area above the piston has to be large. Because high compression needs the combustion chamber to be as small as possible, the flathead design does not permit effective compression. I-head. The I-head arrangement is an overhead design that places the valves over the piston in the cylinder head, but leaves the camshaft and lifters in the block. In this arrangement, the air-fuel mixture feeds into the engine, and burned gases are exhausted through the cylinder head, so the engine gets better compression and can breathe better. The I-head is a more efficient engine and has higher compression ratios than the L-head.